So I think we'll get started. So first of all, I want to welcome everyone to our GPC seminar series. And it's my great pleasure to introduce Raf, our speaker today. So Raf is a faculty member of the MIT Earth, Atmosphere, and Planetary Science department. He's a director of MIT Program of Atmosphere, Ocean, and Climate. And he's a physical oceanographer, looking into the circulation of the ocean and its interaction with the atmosphere and climate. As you will probably see today, he used a combination of observations theory and numerical models to investigate oceanic motions from scales of centimeters to thousands of kilometers. And Ralph has won various awards, like without listing all of them, I think we will just go ahead and welcome Rob to speak with us. And Rob, feel free to take it away.
Okay, thank you so much. I am going to talk a bit about work that we've done in our group on trying to improve our understanding of the deep ocean structure, what I mean, the distribution of temperature, salinity, and particularly buoyancy, and the associated overturning circulation, so the circulation in depth, latitude, space. So first I want to motivate a bit the overall work, trying to explain a bit how the deep ocean plays a role in climate, so to understand why we think that this is an interesting question, and it's interesting both intellectually but also practically because it has implications for how we understand the overall Earth system. So interesting. So as a first simple test case is just to make the case that the ocean is a huge reservoir of heat. And so this picture that I show is a function of depth and latitude, the section across the Pacific collected with a number of vertical profiles taken from a ship that went all the way from Antarctica to the Bering Strait as part of the World Ocean Circulation Experiment in the 90s. And what you see is temperature distribution. So the ocean can be thought of as a set of layers of decreasing temperature, the coldest temperature at the bottom, and then the temperature is increasing as you move upward. But if we ask how much heat the ocean contains, we get a number that I plot here. For every degree Kelvin, the ocean contains the order of 5 × 10⁻²4 joules. So every degree Kelvin you increase in the ocean would give you 10 to the order of what is called order 5 yotta-joules. That's 3 orders of magnitude more than the atmosphere. So clearly the ocean plays a big importance as a reservoir of heat. That big reservoir contributes to long memory in the overall system over thousands of years, as opposed to an atmosphere-only planet that didn't have this reservoir. And in terms of where this heat is stored just by volume, most of the heat is stored below 1,000 meters or so, just because that's where most of the volume of the ocean is. So that's why we care about that large reservoir, especially in long time scales. And I didn't mention it, but the reason why the ocean stored that much more heat than the atmosphere has to do with larger heat capacity, but even more because it's just denser, so there is more volume. The deep ocean is also a very large reservoir of carbon. Again, if you look at below 1,000 meters, this is the same section I've shown before, but now we're looking at dissolved inorganic carbon. And if we look at the yellow values are the largest values. So again, below 1,000 meters, it's where most of this carbon is stored. The ocean stores of around 38,000 gigatons of carbon compared to the atmosphere. Here it's not updated. We're already at 100 gigatons in the atmosphere. But again, it's a very large fraction of the carbon is stored in the deep ocean. So again, we need to know a bit the distribution of properties in the deep ocean and the circulation that move carbon in and out of the deep ocean if we want to have a good understanding of the partition of carbon between the ocean and atmosphere, and therefore of their overall Earth system. So I want to start a bit by giving us overview of what we know from observation about the structure of the ocean and its circulation, because that's what we want to be able to understand through the talk, both with theoretical argument at the beginning and then with a number of observations as we move along. So what about the ocean stratification? Now, this is against the same section I've shown you before, but now I'm showing neutral density. The neutral, you don't have to worry too much about it if you don't know what neutral density is. It's just the ocean density, but taking away compressive effects that do not have dynamical implications. So again, it's the same picture as before, but now I'm showing density. And so the ocean can be thought now as a set of layers of increasing density. So it's a pancake of layers of increasing density as you move from the surface to the abyss. I would call the upper ocean is the part of upper 1,000 meters or so of the ocean, which is strongly influenced by winds. The effect of the winds on the ocean can be seen by this strong deflection of density surface. Clearly, they are not flat as they would be in equilibrium without any forcing. They are deflected from equilibrium by the presence of winds that generated convergences and divergences in the flow pattern that push and lift waters at different latitudes. And this is something that theoretical oceanographers had developed a reasonably good understanding of. Joe Pedlowski being one of the principal contributors to these theories, who I see is online, but also Peter Rines, Billy Young, Henry Stommel. What we are going to focus mostly today is instead of this layer below, that I said is the largest volume of the ocean, probably between 1,000 and 3,000 meters or so. Here, the density surfaces are pretty flat. If I'm looking at the portion of the ocean which is in the Pacific, this is a section, maybe I didn't mention it, but these are all sections across the Pacific. In the Pacific basin, these density surfaces are pretty flat, but we want to understand what is their vertical variation, what sets these vertical variations. If we look even deeper in the ocean, the structure again gets deformed quite a bit. The density surfaces are not flat anymore in that part of the ocean. Their topography starts playing a fundamental role. It's just that this black area is the topography along this particular section in the Pacific. But as you can imagine, there is a lot of structure laterally, so waters are a bit more constrained. They cannot remain as flat. There is a part of the ocean which we call the Southern Ocean to the south of the Pacific. That's quite different from anything else. You look north of it. The reason being that this part of the ocean, we don't have closed basin. Water can circulate around the hub in what is called the Antarctic circumpolar current. And as a result, you see the winds now exert a very strong influence on the stratification all the way to the deep ocean. So it's not just at the top like it was in mid-latitudes, but now these tilted density surfaces are tilted all the way down. And when there is a tilted density surface, because of pressure gradients that are generated by these tilts due to density variations, you generate a current that is pointing towards us in what is called thermal wind balance, or if you want, in geostrophic balance, a balance between the Coriolis acceleration and pressure gradient forces. But most of the talk will focus on this mid-depth that we want to really understand, and we claim, I'll try to claim that we still have a preliminary understanding of what sets those structures, but they're quite essential if we want to understand the heat, salt for that matter, and carbon distribution in the deep ocean. Together with that stratification, there is also an associated circulation, again, in depth latitude space. This is a reconstruction based on what is called a state estimate of the ocean, the echo state estimate. This is in particular from a paper by Russell Chessy and Miguel Forget that use this data set that assimilates all available observation, or a very large set of available observation on the global ocean, to reconstruct now the zonally average circulation, what it means that they take all velocity, they average along a full zonal direction in the upper panel in the Pacific. Differently from the panel I've shown you before, now the author have stretched the upper part of the depth contours of the depth levels to give more information about the surface, and the 1,000 meters is about this depth, and then everything else is compressed below. What you see, the contours are now lines of, they are stream function of lines along which the flow is moving. And in the North Atlantic, you see that there is sinking of water at high latitudes. This water moves essentially along horizontal lines. And if you remember, horizontal lines are also lines of constant density. So this water moves essentially along constant density and then upwells in the southern hemisphere in the region of the Antarctic circumpolar current. This circulation is largely very close to the 1,000 meters, just below the 1,000 meter line. Instead, there is a circulation deeper down below this one, where water sinks around Antarctica again, because of very strong buoyancy loss. This water sinks all the way to the deep ocean. This water, in order to conserve mass, has to return back to the surface, and that requires that it crosses density surfaces. So this deeper circulation is different probably from the circulation in the North Atlantic, in the sense that it must have a stronger, what we call in oceanography, diabatic component, meaning cross-isopycnal component. If you look at the Indo-Pacific Ocean, so now the zonal average is taking only along the Indo-Pacific basin, we only have this deeper cell with water sinking around Antarctica, entering into the Pacific Ocean, and then upwelling and coming back to the surface. So again, this circulation has to be completely diabatic. You'll notice that there is a discontinuity across this line. This line is essentially the northern edge of what we call the Southern Ocean. It's, I guess, the latitude South Africa. And south of it, we are taking an average along the whole zonal ocean, because you can take it doesn't make sense to take an average only over a sector, because the ocean is all connected. While north of it, this average is only along the North Atlantic, and this is only around the North Pacific, the Pacific basin. So you see this discontinuity because the zonal averages are different. Okay, so this overall picture is something that oceanographers have known about for a long time. It's just been refined. We know a bit more about the details. But already in the early days, this structure, both the presence of a stratified ocean interior, which is not trivial. You might think that if the ocean was nearly stationary, you might think that only the upper ocean has some density variation, but instead the density structure seems to propagate pretty deep, and that was known. And it was also known that there was an overturning circulation that was largely inferred from tracer properties. You could see tongue of high salinity entering from the North Atlantic into the deep ocean, and similarly, low salinity water extending from the Southern Ocean to northern latitude. So there had to be a circulation transporting those properties. So how did people go about interpreting those observations? And here I'll just be very quick in giving a few of the highlights. But I think one of the first important contributions comes from Henry Stommel, that correctly makes the point that it's very clear that there are some regions where water sinks to the ocean abyss, and you can see that from just tracer properties that are carried around very quickly, but you don't see any obvious evidence of water being brought back up to the surface. So Henry Stommel posited that if we look, for example, and apply his argument to the Pacific Ocean, he said, well, there had to be water sinking at high latitudes. This would be the water sinking around Antarctica, and said, well, that must be balanced by upwelling in the rest of the ocean, and probably uniform upwelling. And he could estimate what was the uniform upwelling by saying that if I know how much water is sinking at high latitudes, which I could estimate, or they were at least estimated the order of magnitude, and I divide by the area, I can get some estimate of how strong is this uniform upwelling in the rest of the ocean, which he estimated around 3 meters per year. A very small velocity. Indeed, horizontal velocities are many orders of magnitude larger than that. And that would have explained why you don't really see tracer signature of this circulation, because it's just much weaker than other aspects of the circulation, but it should be there, and then it should be at least be acknowledged that Stommel used this insight to actually make arguments based on angular momentum conservation to explain what that implied also in terms of the horizontal structure of the ocean, and making very important contribution in our understanding, for example, the generation of deep boundary currents. But that's not what I'm going to discuss today. Here, the main point is, indeed, there should be an upwelling that balances the sinking of water, for example, in the Pacific Basin. Monk, a decade later, tried to build on this idea, suggesting that since the ocean depth is stratified, meaning density is changing in the vertical, if there is an upwelling, these waters must be changing density as they move towards the surface on these long time scales. And so he said that, well, then we can posit that on top of the conservation of mass, we also have a conservation of buoyancy budget. And he said that given the density surface in this mid-depth range, so we're talking between 1 and 2 kilometers, where the horizontal density surface are nearly horizontal, then the advection term is mostly this vertical velocity crossing density surface, so WdBdz. This is the vertical advection of water that is crossing density surfaces. And B here is buoyancy, so buoyancy is just a rescale density. I take the density, I divide it by some constant density, multiplied by the acceleration of gravity. So essentially the effective gravity experienced by the water, but let's call B as buoyancy as a proxy for density, except for a change of sign. It's minus density. And Walter Munk posited then that there is this advection diffusion balance on the right-hand side. He said, as the water is moving up, there must be some heat, or in terms of buoyancy, really light water being diffused downward to allow this water to becoming lighter as it crosses density surface. And he just used classical Fickian diffusion law. So DdZ of kappa. Kappa is a diffusivity, the rate at which heat or buoyancy is diffused in the ocean interior, time dBdZ. As we said, he had no reason, there was no evidence that W would be confined to any particular region as far as he could tell. So he assumed that this was constant, and also this kappa, this rate of diffusion, any additional information could be assumed to be constant. And if these two coefficients, W naught and kappa T, are both constant, this equation has exponential solutions. So the solutions are given by an exponential of Z divided by an E-folding scale, which is the ratio of the diffusivity to the upwelling velocity. So now Walter Munk was pushing this line of argument because he had observation from the Pacific Ocean in mid-latitudes. And these are the profile that he actually used in his publication, this paper. This is depth, and the dots are measurements of, in this particular case, potential temperature, but he also used density. And you see the dots that are decaying with depth, meaning that the density is becoming higher, or the buoyancy is decreasing, or the temperature is decreasing. And the black lines are exponential fits to the dots. These exponential fits are the E-folding scale, or so the exponential fit gave him an E-folding scale, which, as we said, was an estimate of kappa over W naught, and it turned out to be around 800 meters, at least for the Pacific Ocean. So at this point, using the estimate of W naught that Stommel had been using, or that the community had been using, then you can estimate what kappa T is, that you just multiply W naught by 130 meters, you get a value of 10 to the minus 4 meters squared per second. I should pause a second and say that actually Walter Munk went beyond this. He used two independent tracers afterwards, using both temperature and delta C14, an independent tracer with different, they satisfy a different equation because it also has a decay rate and it has a different distribution. So he had two independent estimates of two different E-folding scales for the two tracers. And so he could estimate independently both W naught and KT and got a similar result. So why was this result important? Well, this kappa T of 10 to the minus 4 meters squared per second is 3 orders of magnitude larger than molecular diffusion of heat, for example. So that strongly advocates for a turbulent process to be responsive to the rate at which heat is diffused deep into the ocean. If one used just a molecular value, essentially one would have that the stratification of the ocean would be very much confined to the surface and not spread out as deep as observed. Now, the question was, what generates these strong turbulent diffusivities? And Walter Munk realized that large-scale ocean flows tend to be associated with what we call large Richardson number, if we want, but with characteristics that led them to flow mostly along density surface, definitely not to generate instability and mix across density surfaces. And so he posited that it's probably smaller scale motions like internal waves. Internal waves are just waves that you can think about them as oscillation between layers of different density, much like surface waves are oscillations at the free surface of the ocean that separates the ocean layer from the atmospheric layer. And this motion can actually generate overturn. They can generate small Richardson number, and so they can generate mixing. So the idea was that probably this means that these small motions play an important role in mixing heat and buoyancy from the surface to the interior and maintain this deep stratification. So now I've given you a bit of an idea of what the historical context was. Now I want to see what about the assumptions that are made in the arguments of Stommel and Munk do hold to more modern observations, and how, based on that information, do we need to revise some of those arguments and update them to account for observational evidence. So the first one that I want to start from is the one that generally gets dismissed, I think, a bit unfairly, and it's the statement that the stratification in the ocean is exponential. So here I'm looking at the section in the Pacific. Again, it's the same section as before, except that I cut out the Southern Ocean because we want to focus on this depth range between 1 and 3 kilometers. And I'm going to plot stratification. Stratification is n squared here, which is just G over R naught. The sigma dz here, sigma is density or potential density. And as we said, I want to test whether this stratification is exponential. So it decays as Z over H, where H is some unfolding scale. And so here I'm plotting indeed the stratification on the versus depth. So depth on the vertical axis and stratification on the horizontal axis. And I'm doing it for a latitude of 20 degrees, a latitude 20 degrees south, 20 degrees north, and 45 degrees north. We're going to use, again, WOS data. And I'm going to take average of the density stratification for each depth, or technically along each density, along a whole zonal circle in the Pacific, Indo-Pacific here. And so every dot is an estimate of the stratification, and I'm using a logarithmic scale on the horizontal axis. So I'm plotting really the log of n squared, and that should go linearly as Z over H, linearly in depth if the stratification is exponential. And so these dots are pretty much following along a clear straight line. I should acknowledge it was Elliot Zipperman that reminded me that I should take the exponential stratification seriously. They've done some work, again, making the same point. And what you see, this is true at all these latitude ranges. So the inside that the stratification is exponential in this mid-depth range is indeed very well supported by more modern observation. This is true for density. Walter Mann published a recent paper showing that that is not necessarily true for temperature or salinity independently, which are the two tracers that contribute to setting the density of the ocean. This difference is important because density is a dynamical quantity. It affects dynamics, while temperature and salinity independently do not. It's only to the extent that they affect density. So there can be temperature and salinity distribution that result in no density effect. For example, water can be very warm and very salty, or very cold and very fresh and have the same density. So there are patterns in TNS that don't have density impact, and those are not exponentially in their vertical profile. But what we want to understand is, why is this stratification exponential, and to see whether Walter Mann's argument indeed is consistent with the other piece of evidence that he used. By the way, I should point out that the stratification is also very exponential in the South Atlantic. The North Atlantic it depends on the latitude you look at. There is a big intrusion of Mediterranean water in the North Atlantic that affects a bit this profile. So it's a different source, and we can comment at the end of why that would break the exponential stratification based on dynamical arguments. So what about the other lines of argument that Mann used in explaining or providing an argument to explain the exponential stratification? Well, one was assuming that the mixing rate, this kappa T, this effective diffusivity, was essentially constant through the ocean. And we can start looking at that is actually true in most of the ocean. This panel on the left-hand side from Waterhouse et al. Is based on measurements of turbulence, now with very precise turbulent probes that are lowered all the way to the bottom of the ocean from the surface. And these are a profile of kappa as estimated from depth above the bottom. And so average of the depth above the bottom, but coming from a number of different places in the ocean. This profile, the red one, is the most typical one that you find on flat bottom topographies of order. The problem is that it's of order 10 to the minus 5 meters squared per second, a whole order of magnitude too small to account for the stratification that Walter Mann was trying to explain. However, you find that every time you are on young topography, let's call it, or rough topography, the profile of mixing seems to increase towards the ocean bottom. And in this case, it can become even an orders of magnitude larger than what Walter Mann had estimated. And so where does that happen? Where is it that this profile all of a sudden seems to have a strong vertical variation? And this is an estimate from De la Vergne et al. They use a global model to essentially estimate where they expect strong turbulence. And these bright colors is where the kappa essentially is very large. And you see that it tends to be large in places like the Mid-Atlantic Ridge, the South Pacific Rise, or the Mid-Atlantic Ridge, the ridges in the Indian Ocean. We do understand why that is the case. These large value of diffusivity are generated by tidal motion primarily, at least in closed basins. Tidal motion moves the ocean back and forth. And you remember that I said the ocean can be thought as a set of layers of increasing density towards the ocean bottom. But think about each one of these layers, when it's at vector of a very rough topography, it starts oscillating back and forth. And so you generated an internal wave, as it is called. And these internal waves, as I said, can break, and they tend to break closer to the topography where they are generated. So now we understand that there is both lateral variation in eddy diffusivity, and in particular, importantly, very strong vertical variations. So that seems to be a bit of a problem for the argument of Walter Munk, because it seems that argument relied on kappa being constant. So we'll have to come back to that. But even more importantly, and I should point out that this is something that the community has realized, that this might be an issue in terms of explaining the exponential stratification. But I find the second line of argument that is even more powerful, probably more obvious, is that if I go back and look at the overturning circulation for the Pacific, if we are focusing on the Pacific, again, this is streamlines, and you see that water is sinking around Antarctica, entering the Pacific, it rises towards the surface, but by the time you are at 1,000 meters or so, all this water comes back and upwells in the Southern Ocean. So the vertical velocity itself, W, is also decreasing very rapidly in the vertical, from a maximum value a bit below the mid-depths, a bit below 3 kilometers, and essentially to 0 by the time you reach the top of the mid-depths at 1 kilometer. So now there is an issue that both W and kappa are, at the very least, vertically dependent, probably also horizontally dependent. But let's stick to the vertical dependence first, because if we assume the density surfaces are nearly flat, horizontal gradient don't really matter. But the vertical gradient clearly matter. We are trying to explain the vertical stratification. And clearly, the exponential solution that Walter Munk was describing required W and kappa to be constant. So how can we move and try to reapply that argument, but to see how we can reconcile this vertical variation in W and kappa with the vertical profile of density, which is exponential in the ocean. And this is what we've done in our group. At least what I'm going to present here is what we've done in our group with a couple of students, Mason Rogers and Ross Verves, and Louis-Philippe Nadeau, who is instead a collaborator at Rimouski in Canada. So let me start introducing how we are approaching the problem. First, I'll show you a very idealized numerical simulation, just to set the stage for what we want to explain. This numerical simulation is in a basin. This is a basin, these are lateral walls that extend from the surface down to depth. So we are having a closed basin and a re-entrant channel to the south, meaning the water from this side will re-enter. The exit from this side will re-enter from this side. So there are no walls here. There is a wall to the south. This basin is filled with water. We are blowing winds at the surface. So this is the wind pattern that we are blowing. It's only on the southern hemisphere. It's over the southern portion of the domain, because as I said, there are also winds blowing at higher latitudes, but these winds affect the upper layer of the ocean. Here we are interested in the mid-depth, and we are trying to use the simplest models that we think can capture the dynamics we are interested in without adding additional complication of surface wind-driven circulation in the basin. We also prescribe a restoring to a buoyancy profile, a density profile. It's very cold or very dense to the south, it becomes warmer, and then we don't have any density variations north of the basin, because again, we don't want to create structure. We are interested in seeing how the structure develop in density without any forcing in mid-latitudes, because we assume that most of what we see is set by circulation that develop in the southern hemisphere. So now here I'm showing two pieces of this solution. Well, maybe I should point out this model is the simulation run with the MIT GCM model on a 2 by 2 degree resolution and 40 vertical levels configuration. That's pretty coarse. As a result, we had to parameterize a lot of processes. For example, convection is represented through convective adjustment. We mix in the vertical every time the density, the vertical density structure is statically unstable. We have a closure for baroclinic instability, the Gentile-McWilliams closure, which is just telling us that when there are lateral density gradients, there is a tendency due to baroclinic instability to flatten these density surfaces, and we use a constant coefficient for this term. And instead, what we're going to vary is the vertical profile of the turbulent diffusivity, because we want to ask how that vertical profile impacts the stratification and the circulation, and to see to what extent, this is an important parameter, which we now found out that is variable, it's not constant. If I run for a moment a simulation with a typical low value diapicna diffusivity, but constant, just to give you an idea about the kind of solutions that we get. The black lines are density surfaces. And so you see the density surfaces are tilted over the Southern Ocean because of these strong winds that generate strong upwelling on one side and downwelling on the other. So they tilt the isopycnals up. But the isopycnal instead in the closed basin to the north, so this part of the domain, are flat, like in the observations. The color contours are, again, the overturning stream function. And so you see water sinking at high latitude and rising in the basin. Again, there is an overturning circulation in the same sense of what we see in the circulation. And then we can look also at what is the buoyancy profile that we get in our solutions. And again, water goes from light to dense. And the two questions we want to ask is, under what condition this profile is going to be exponential? And we get an overturning that has a maximum deep in the water column that decays pretty rapidly by the time you reach 1,000 meters, consistent with observations. And so now I'm showing you two solutions with these models, just to set the stage and understand a bit the differences of where we think we are trying to go. The upper panels refer to a simulation where we use a kappa of 10 to the minus 4 meters squared per second. This is value in blue. This is the value that Walter Munk had estimated. So we're just trying to run a simulation with this value and see in what parameter space we end up in terms of what the solution looks like. And again, this is depth and latitude, and it's our overturning circulation. This is the stratification. The density surfaces are flat. And this is the overturning circulation in colors. Let me start by looking at what the stratification looks like. This is this panel in the middle. Now I'm showing n squared again, the derivative of density with depth. And I'm plotting it log of n squared as a function of depth. And you can see that this is the profile of stratification that we get in these solutions. The folding scale is very deep. It's 1,600 meters. By the way, I should say that the n squared is computed taking the average of n squared over the northern half of the whole basin north of the equator as an estimate. It doesn't matter really where you take it, but we take a big, large average to get smooth profiles. So the folding scale between 1 and 3 kilometers is essentially 2 kilometers long. So that is telling you that this profile is not really exponential. It's a linear stratification. So we don't really quite get the stratification, the exponential structure that we see in observations. Also, when we look at the overturning remains pretty large all the way up to even above 1,000 meters. That is to be expected to some extent because we have very strong mixing even high up in the water column, and mixing is what allows water to rise to density surfaces. So we are allowing quite a bit of water to upwell to pretty shallow levels. So the main point here, take home point, indeed, if you use a constant kappa, we don't get a solution that is quite consistent with neither the structure of the overturning nor the structure of the stratification, which was our goal. And maybe I should point out that the last thing that I can point out, this is depth, and the blue curve is the profile of kappa, but the red curve is the profile of W. The profile of W from the solution, the vertical velocity. And you see the vertical velocity is not quite constant. So that is why Walter Monk's argument doesn't quite hold. W is varying in Z, and that is what makes the solution not quite exponentially stratified the way one may have expected. Now let's look at the solution in the lower panel. This is a case where instead I use exponential profile of kappa, which we take to have any folding scale of around a kilometer. This is inspired by averaging available profile of vertical mixing in the global ocean and averaging at a fixed depth, so to reconstruct a vertical profile. And so this blue line is as a function of depth and the value of kappa that goes, I think I cut out the upper portion here. It goes from 10 to the minus 5 to 10 to the minus 3. So we have a kappa profile that starts from values of order 3 10 to the minus 5 and gets to values of 4 10 to the minus 4 meters squared per second at the bottom. So it's smaller than Munk value at the top, but definitely larger than the Munk value at the bottom. Now let's look at what solution we get for this vertical profile of kappa. And we get an overturning circulation that is more confined to depth. But more importantly, let's look at the vertical stratification, the distribution of density as a function of depth. This is what I'm plotting here, log of n squared. And now this line looks pretty straight. It's log of n squared versus depth. So the profile is quite close to an exponential. The folding scale is of order of 650 meters. It's a bit less than estimated by Walter Munk in the Pacific, but this is a pretty idealized solution. But we start getting clearly a solution that has something close to an exponential stratification and overturning that is confined to depth. So the first question is, how can it be that I have now both doubly, maybe let me point out, let's go to this panel, and the vertical velocity now, it's also vertically varying. Right? This is the profile of vertical velocity as a function of depth. And also that is varying in z. So how can I get an exponential stratification now that I have both a vertical variation in W and a vertical variation in kappa? Well, it turns out, and if people are interested, there is this paper by Rogers et al. Where we just showed the simple algebra that you can solve this advection diffusion balance posed by Munk, meaning W times dB dz is equal to the diffusive term. It can be solved also for W and kappa that are z dependent. And it turns out that the exponential or the terms that appear in the exponential function for that solution depends on the ratio W over kappa. So as long as W over kappa is a ratio or a constant, meaning the W and kappa change more or less at the same rate, the ratio remains a constant, and therefore you have still an exponential stratification. So you can have W and kappa varying in z and have an exponential stratification as long as W and kappa co-vary. And this is a bit what you see here. They are both decaying pretty much exponentially fast within this mid-depth range. I like to move a bit beyond these were very idealized solution. The first thing I wanted to check is, well, what about if we apply the same argument now for a more realistic simulations? So let's now look at the simulation that uses the same MIT general circulation model as before, but we're going to include the realistic topography and realistic surface wind forcing at all latitudes, and realistic forcing in temperature and salinity, while we technically use restoring to temperature and salinity profiles from observations. We use in particular the profiles as estimated from the echo state estimate generated, I guess now at JPL, but originally here at MIT. So we have a more realistic simulation, and we still have to prescribe the vertical profile of kappa. Now we're doing it in a more principled way, meaning that we express the vertical profile of kappa as a function that decays as height above the bottom, because we know the kappa is largest close to topography, and then decays with depth. But of course, the topography of the ocean moves up and down where there are ridges, seamounts, shelves. And so we're going to have a self-similar profile as a function of depth, with an folding scale now of only 600 meters. That's inspired more or less by observations. We played a bit with this number because the observations say anything between a few hundred meters to maybe 600 meters. But the qualitative results don't change too much. So now, by prescribing this profile of kappa, we actually have a profile of kappa which is varying both in the horizontal and in the vertical, because the vertical profile is different as a function of depth above the bottom. So now it's a pretty more complex regional distribution of kappas. And we run our simulation. This is the result that we get. This is the overturning circulation and the stratification for this more realistic simulation with full bathymetry. And I want to show you that, first of all, the structure of the overturning compared to the echo state estimate. This instead is a model. It's the same MIT general circulation model, but this is constrained with observations, all available observations to the group. And so it's a reasonably good estimate. It's one of our best guesses at what the structure of the overturning is. And I would contend that these two profiles are not terribly different from each other. We have this overturning that decays by the time we reach 1,000 meters and expands all the way to 40 degrees north or so in the Pacific Basin. So now we can look at what is the stratification in our realistic simulation. Well, this is again as a function of depth, the log of n squared. And you see there's a pretty straight line, has an folding scale of 750 meters. We are taking the stratification or the folding scale for the whole ocean north of the equator the value that Monk had gotten was at a particular latitude. That changes a bit with latitude. So it's very consistent with the estimate you would get from echo instead. The stratification is exponential. Now let's look at the profile of kappa. Now, be careful that now the profile of kappa is not the profile I'm prescribing here. Now I'm taking the average profile of kappa at a fixed density in the Pacific Basin. And so I'm averaging over all the spatial patterns that emerge because of variation in topography. And so the E-folding scale of kappa is, well, kappa has an exponential profile, and its E-folding scale is closer to a bit more than a kilometer and a half now. And W, the vertical velocity, is also decaying exponentially, and the ratio of the two is pretty close to a constant, and that results in that close to exponential profile. So indeed, it seems that at least the qualitative argument is the fact that W scales with kappa is what allowed the stratification to remain exponential is the key result, and allow us to explain why you should get an exponential stratification. By the way, here I'm only showing a solution where we used a profile that depends on Z with the student Ross that I mentioned before. She also looked at spatial variability where we allow mixing only where there is stronger topographic feature, for example, between the northern and the northern portion of the Pacific Basin or not, and you get very similar result. If there are regions where mixing is small, they don't affect the solution much, just to get the same similar result. So I want to point out, however, that there is a fundamental difference between the idealized simulation I've shown you before and this realistic simulation. And what is the fundamental difference? Well, let's think for a second about Monk's budget, but now applied locally at a particular location in their realistic simulation. Here I'm just rewriting Monk's budget as dividing, you remember it was WBZ is equal to the DZ of kappa BZ. I can rewrite a budget for W over kappa, dividing both sides of the equation by kappa, and I get the W over kappa, so the ratio of the upwelling to the ratio of kappa at every particular depth is given by the E-folding scale of kappa, kappa Z over kappa, and the E-folding scale of the stratification, second derivative of BZ divided by BZ itself. Now, in every individual profile, the decay of kappa is pretty sharp, an order of 600 meters, while the E-folding scale of the stratification is actually larger. Now, remember that kappa is decaying with depth, while BZ is increasing with depth. And so the sum of these two terms is dominated by the kappa E-folding scale. It's negative. And so that would suggest that W is negative. That's opposite to the picture I've shown you before. So we will have to understand why is it that W in the net is positive, but locally it seems that the budget would suggest that it's negative. And I can compare this to the average budget along an isopycnal, so the average of W over the average of kappa, now average over a full isopycnal, which is a bit more similar to the idealized simulation that I was using when I didn't have any topography. And that is given by the E-folding scale of the average kappa. And the E-folding scale of the average kappa is close to 1,600 meters, much larger than kappa Z over kappa. And why is that? Well, because this case mostly with the folding scale of the topography, because values are always large close to the topography, and then they decay above the topography itself. And structure like the Mid-Atlantic Ridge have a scale of around 2,000 meters. So this is what sets the folding scale of kappa itself in a global simulation. And this is indeed the folding scale we use in the global simulations to mimic the effect of topography. And then you also have the term that is proportional to BBZ over BZ. This, I don't put the angle bracket because B is pretty flat in the basin. So taking an average of buoyancy along buoyancy surface doesn't really make much of a difference. So now you see that if I look at the large scale budget, the folding scale is the dominant term and it's positive, and this term is negative, and all of that smaller. And so in the net W average over a full isopycnal is divided by the average of kappa, which is positive. It's a positive term. So how do we reconcile that? Locally, seems that water should be sinking, but on an average large-scale basin scale, it should be rising. And that seemed to be a fundamental difference between the more realistic model versus the simple idealized model. And why is it that, however, they give me a large-scale pattern that seems to be similar? And that's work that we've done for a while and trying to make the point that now, look, And what happens now, I'm trying to look at the local buoyancy budget of Monk, but now trying to interpret a bit more mechanistically. Think about the water parcel that is experiencing this vertical profile on mixing that is increasing toward the bottom ocean topography. Well, that means that this water is being mixed more vigorously with deeper water, which are denser, and less vigorous with upper water, which are lighter. So as a result, this water is getting deeper, and that's why it's sinking. That was the argument. Why is it the W is sinking? Well, because if the rate of mixing decays increases fast enough with depth, that will dominate the direction in which water has to move. However, when water finally sink all the way to the ocean bottom, water are only going to be mixed with water above it, which are lighter. There is no mixing, or if there is any mixing, there is no mixing with waters below. If anything, there is some geothermal heating if you're in regions that are geothermally active. So this water definitely becomes lighter. And so now if you're thinking about waters that are over a slanted topography like along a mid-Atlantic ridge, well, this water is getting lighter and then it can slide up towards the surface. So the claim is that when you use this more realistic configuration, the W is not just responding to mixing, it's a more complicated pattern of water sinking in the interior and rising along the topography. So now, one of the questions was, is there any evidence for this? Oh, I had to accelerate, for this happening in the real ocean? Well, then I'll skip this slide in the interest of time. Yes, there have been previous experiments that have shown some rate of sinking in the ocean interior consistent with the first part of the picture. But here I want to push a bit the second part, that we haven't had yet direct observation of the rising of water along bottom topography. And so a large observational experiment has been conducted now for last, well, it's 2 years up to 2022. We call it the bottom boundary layer turbulence, the BLT experiment. And what I'm going to show here is mostly work that has been done by Bethan-Winnie Katanak, a student at Scripps who is about to defend her thesis partly on this work. Yidong Fangxi is a postdoc here at MIT that has done some of the analytical and the numerical work. Matthew Alford and Alberto Navera Garabato that really led the observational work in what I'm showing here. Kurt Polzin and Marie-Jose Messias were other critical contributor to the development of the experiment. I was involved, but I didn't do any of the observations. So I shouldn't take credit for anything. What I'm showing here, we went to the Rockall Trough. It's a pretty deep trough in the North Atlantic, so close to 2,000 meters deep. Has canyons along the side and a strong tidal flow. So we expect generation of very strong tidal motions. And the idea was to put a tracer, in particular a dye, in one of the canyons, in a canyon so that it remains confined and we can sample it in time and see whether it's true that indeed, since there should be this bottom enhanced mixing generated by tidal motions, we expected the mixing to drive strong upwelling along the canyon. So here we show the result from this dye release experiment. The dye was released at the bottom of the ocean. So this is time since the release, and the contours in black are temperature isoline. In green, if you see, is the concentration of the tracer, and the purple is an estimate of the rate of turbulence, how strong was turbulence at that time. And this is time since the initial time. A ship is cruising along, trying to sample the tracer with a fluorometer to see where the tracer is. And what you see is that there is a big plume. There seems to be a big, strong mixing event happening all of a sudden, where tracer is being lifted up and being mixed order of 100 meters above the bottom. If you go sometime later, the ship was going back and forth in the canyon after the tracer was released. Now you see that the tracer gets spread along the canyon quite a bit. There is a very strong tidal flow. There is moving tracer up and down. There is sometimes some mixing, but now the tracer is spread at least over 100 meters after 18 hours from the initial state. Now the problem is that how do we quantify whether the tracer is moving across density surfaces, given that the sloshing motions are moving it up and down very vigorously over the whole canyon? Well, not the whole canyon, but a large fraction of the canyon. Well, one way is to plot the density of the tracer in potential temperature salinity space, or essentially in temperature salinity space. This is potential temperature, this is salinity. The black lines are lines of constant density. If I move along this line, the water gets warmer but saltier, and so the density doesn't change. this arrow, the star here, is the value of temperature salinity at which the initial tracer was released. And then we look as a function of time since release. So the color contours is how time is evolving. We are moving from here to there. And the radius of the circle is proportional to the concentration of the tracer. At the beginning, the tracer is very concentrated. It hasn't been diluted yet, but it already moved after a few hours to slightly different temperature salinity space. If you keep following it, you see the circle becomes smaller, the tracer gets diluted, but you also see that the tracer, and this is the barycenter, the center of mass of the tracer in temperature salinity space, you see that the center of mass is really moving farther and farther, crossing density surface, getting lighter. So indeed, this mixing is driving an upwelling across density surfaces along the canyon. We can estimate the vertical velocity associated with this motion is over 100 meters per day. It's very fast, as it should be, because if you think that most of the water upwelling in the global ocean have to upwell along the sloping topography, where it has to be pretty vigorous flow right along topography. How does the mixing actually occur? That's an interesting story, and I'm very close to being done. Here, I'm looking now at mooring data that measure velocity profiles with an ADCP over the first 200 meters above the bottom topography. This is the bottom topography, and you see blue is velocity down the canyon, red up the canyon, and you see this flow flipping back and forth. This is the tidal flow at the M2 tidal frequency. And the flow in particular, what is most important for us, you see that the velocity are weaker at the bottom, but they increase with height above the bottom. And so during the upslope phase, in this particular location, you have a positive shear. Why is the positive shear important? Well, you're advecting cold water over light water, because you're advecting water from below deeper density in the canyon. The canyon is slanted. So water from deeper part of the canyon is denser, and you're driving this water over lighter water. So you can generate convective instabilities during this phase, or shear instabilities. While when the flow is down the slope, you have a positive shear. So after you create a mixing event, you re-stratify the ocean by bringing light waters from up the canyon over the denser waters. And so the idea is indeed that you should get these overturning events followed by re-stratification. And just, this is the last slide, I think. I'm now showing again from mooring data, now the temperature distribution as a function of time. This was a very high resolution thermistor chain provided by Hans van Haren. And we are looking at the temperature profiles, and you see this temperature surfaces are nearly flat here, and then all of a sudden they plunge. This is one of the times when the strong vertical shear is developing, and it's a positive shear, and it drives an overturn. Here is an estimate of how strong the mixing is with turbulent probes, and you see there is strong mixing rate associated with this plunging isopycnal. And here we're also plotting the distribution of tracer that was measured with a fluorometer from a ship at the same time, at this time here. And you see that when there is this strong mixing event, you also see the tracer being mixed up the water column. So it's really this intermittent mixing event that happened during a particular phase, during the positive shear phase of the tide, that drives this mixing that allow waters to slide back toward the surface. So we do find evidence for this W to rise above the bottom. To conclude, I think I didn't discuss much the theory that we are working on explaining why W is related to kappa, and that relies on combining a theory for the Southern Ocean with the theory for the interior ocean dynamics. You can find why W scales with kappa, as you might expect, because it's kappa that allows waters to be upwelled in the ocean basin. But I think an important point that is really worth emphasizing is that there's been a lot of discussion of what some call missing mixing. The 10 to the minus 4 meters squared per second that Walter Munk is talking about is found close to topography, but not much further up in the water column. And we contend that if you buy our argument that it's W over kappa that has to remain constant to have an exponential stratification, well, you would definitely expect that since both W and kappa are decreasing, the kappa value should be pretty small by the time you reach 1,000 meters and already at 2,000 meters. So the fact that kappa value are small in the ocean interior is very consistent with the fact that we have an exponential stratification. And to explain that exponential stratification, you really need this exponential profile of kappa, otherwise you would not get it. And we show simulation that definitely show that. And then I started moving towards applying these arguments to a full ocean where topography starts playing a role, because now the upwelling really happens along sloping topography, something that we ignore in the idealized model, but becomes important in a theory that accounts for topography. And I'll stop here and ready to take questions if there are any.
Thank you, Raf. And hello.
Hi.
There are a couple questions from on the Q&A box. Do you have access to those, or should I read them?
Yeah. With exponent, not Z multiplicative, but integral is Z with upper limit. I think I'll have to discuss with Ravi to understand what kind of profile he's talking about.